see. Well, yeah, we're really excited to be here and take you into the great beyond. We're going to talk about how we can estimate growth trajectories across the lifespan using random effects models. And we'll focus on a particular type of model called dynamic measurement model, which was developed by Daniel McNeish at the University of Arizona. And the motivation for this type of model really comes from high-stakes cognitive testing. Every year, people around the world take more than 1 billion tests. This includes tests in schools, university admissions exams, or job entry exams. These high-stakes tests are usually single shot, and this is really a problem. So if you take this example data here, we see people's performance on a verbal ability task across ages. Now, imagine we've got 2 people in our distribution here. We've got, oh no, that's not what we've got. Right. So we've got 2 people in our distribution here, and we're measuring them on a university admissions test at the age of 18. So we've got Bill and we've got Bob. And what we can see is that Bill is just below the mean while Bob is just above the mean. So based on our admissions test, we might decide to admit Bob, not admit Bill. But then we are in the lucky position that we get to measure them again a few years later, and this is what we find. So based on this result, we might think, well, maybe we've made a mistake. At the very least, we should have probably admitted Bob. So what this highlights is that single-shot testing is a problem because what we gain at the single event is mostly information about people's past. We gain information about the knowledge and skills they've been able to accrue, and a lot of information about the advantages and disadvantages they've had in being able to accrue these skills. We're not gaining any information about how they're likely to change in the future, and this is really what we're interested in these types of high-stakes cognitive testing situations. So what single-shot testing does is conflating achievement with capacity, and this is particularly a problem for disadvantaged groups in society. For this reason, multiple assessments are much better because they allow us to estimate change over time and give us an idea of how people are going to do in the future. But how do we model them? The most simple approach is, of course, to look at linear growth. So we can, for instance, just fit a linear model and look at the regression line. This looks okay, but we can immediately see that the function doesn't fit particularly well. In fact, what we can tell quite clearly is that there is an asymptote here. And the linear function, of course, can't capture the asymptote. And this is really what we're interested in because cognitive capacity is an asymptotic construct. So capacity is the expected future score once the construct has fully developed. And this is what we're often really interested in measuring when we look at high-stakes cognitive testing. You can imagine it like this. We've got a growth curve, so you're somewhere on that trajectory, you're changing over time, but the underlying capacity that you have to develop this construct is always the same. So in order to be able to estimate this construct, we first of all need multiple measurement points, and then we need the appropriate models. We can use, for instance, dynamic measurement models to estimate our cognitive capacity. So as I mentioned in the beginning, dynamic measurement models were really developed and popularized by Daniel McNeish and colleagues in the past couple of years. And they combine aspects of longitudinal eigen response theory, nonlinear growth models, and dynamic assessment. They're really quite powerful. The S-square from capacity scores are 2.5 times larger than the S-square from traditional IRT scores, which is kind of the traditional approach to assessing capacity. What you can see in these graphs here is on the left, dynamic measurement model estimates compared to, on the right, IRT estimates. And you can see that the correlation between the actual and the estimated scores are much larger for dynamic measurement models, so they're really faring quite well. So what I think is really cool is that we can use these types of models to estimate the shape of development. We know that development can have many shapes, so to start out with, what we need to do is think of candidate shapes. So if we're interested in asymptotes, there are a number of shapes we could choose. This is just a few that are shown here. You can either have a really strong a priori idea of what kind of shape you would want to fit, or you can select several candidate shapes and then run model comparisons and select the most plausible models in terms of the biology or psychology of the construct that you're interested in. And the next step is that you then use this model to estimate capacity and other quantities of interest. And I think this is a really nice feature of these types of models. So we directly get an estimate of the cognitive capacity from all of these models, which is of course what we're mainly interested in. But with some of them, for instance, the logistic, we can also estimate the lower asymptote, which may be of interest, or the inflection point, the point at which the function changes shape. Now, just as a side note, in general, you could use this type of approach to also look at other type of shapes that you may be interested in. Maybe you're not interested in asymptotic relationships, but in peaks. So you could use a quadratic kind of function to estimate the apex, say. But next up, Roger is just going to give you an idea of how you can fit this in practice.
Yes. So if you're so inclined, there's a lovely tutorial from about 2 years ago that basically walks you through how to estimate these models, in this case in R, although you can also do it in things like Python and MATLAB. They walk you through 4 particularly kind of popular R packages. One of the classics is LLME, which has some nice features, including the simplest syntax and relatively fast to converge. LMER has not that much to say in favor of it, according to them. There's another package which is relatively slow, but it has higher convergence for sparse data. So if you have, say, measurement, maybe 3 or 4 measurements for people, but you actually have a full lifespan worth of data, everyone's data is very sparse, and then your models tend to start kind of collapsing or failing to converge. If that's the case, then this particular package seems to do well. And finally, BRMS, which uses Stan and Bayesian estimation. It's increasingly popular. There's some people here at the unit that use it. It has a few nice features, including a flexibility of distributions. You can set your own priors on each of the parameters, and it tends to do relatively well in terms of estimation. Right. It is a bit slow. So I'm going to focus on a subset, i.e. the exponential growth curve and the NLME package, because it's relatively easy to follow along. So what does our data look like? Well, this is the same data we saw before in the kind of spaghetti plot of the lines. So we have verbal performance on this scale that goes from approximately -5 to +5, and we have age, and it's long data. So the same person here is measured on multiple occasions, and we have their performance score on each of these ages. So in this case, the exponential curve, we have a few things we're interested in. Firstly, the intercept, so where do they start, or what's their baseline score? And secondly, the BC or beta C parameter here is capacity. So where, based on the trajectory, based on that we assume growth is exponential, where do we think they'll end up? So we load the package, and the syntax, I'll walk you through it a little bit. So here we're trying to predict performance as a function of your intercept. So where did you start? Your capacity, where do I think you're going to end up, minus your intercept, to kind of scale things. And then we center the age here because the first occasion for some of the people is age 3. That's our data. These are a fixed effect, so these are kind of more standard approach where you'd have an intercept and a capacity of the population, so to speak, and a rate parameter. But most importantly here, we're estimating random effects for the intercept and the capacity. In other words, we're allowing people to start at different points and we're allowing them to end up at different points. One thing that helps convergence a lot is to give you some feasible starting values. So to give the estimation kind of some idea of where you suspect these parameters might end up. So what does our fixed effects model look like? Well, this is the simplest part. So we get the summary here. So we get the intercept. So that's where kind of essentially people start. We get the capacity. So where does the population end up at about a little bit more than +3. And then the rate parameter, which I won't focus on too much. So those are kind of our standard fixed effect population level models. But of course, we're interested in the random effect structure. So what does that look like? So we're going to compare 3 models. Well, firstly, it's the full random effect. So in this case, people are allowed to differ in how where they start and also where they end up. Secondly, we're going to model a fixed intercept and random capacity model. So what that means is that people start at the same place, but they end up at different places. And if you're interested in developmental psychology or psychopathology, there's these ideas of equifinality and multifinality floating around. I think it's quite nice that you can at least come up with ways to kind of formalize and quantify these models that are often discussed more in theory-only context. So this would be an example of multifinality. So we assume everyone starts off pretty much the same, but we allow them to differ in where they end up. And of course, we can then also think of the reverse of equifinality, where we say, well, people might start at different places for a variety of genetic environmental reasons, but we're going to assume that they converge at the same place. This is concept of equifinality, or at least one interpretation of it. So first we're going to fit a model of equifinality. So here we have a fixed effect for capacity. So if we look at the syntax here, oh, I learned something yesterday. This is totally for me. Let's see. Oh, can I do this? Anyway, so here we're going to estimate the random effect for the intercept. So we're going to allow people to differ in where they start, but we're not going to allow them to differ in where they end up, because there's no random effect for the capacity. So what does this look like? Well, then we get a random effect for the intercept, because that's what we wanted. And if we then estimate the predicted scores, you get kind of the predicted trajectories for the population that reflect our theoretical position that actually no matter where people end up, they're going to end up at the same, or start, they're going to end up at the same place. So you can see here that everyone converges on this kind of equifinality, same asymptote. I'll come back later how to compare these models. So the idea of multifinality is exactly the reverse. So here we have a random effect for capacity. So people are allowed to end up somewhere different, but we're going to assume they start at the same place. So again, we fit this model, and then we get a random effect for capacity, but not for the intercept, and then our data looks the reverse. So we assume people early on in life start at pretty much the same place, but we allow them to reach different levels of capacity. And we can use this knowledge to infer based on their score at, say, age 18, where they're likely to end up. And finally, the full random effects model. So this model would test the assumption that people start at different places, but also end up at different places, which some might argue is the most kind of psychologically a priori plausible model. So in this case, we end up with a random effect structure that gives us both of these, the intercept and the capacity as random effects, and then we can plot the predicted scores and see what they look like. And I think these are relatively close, quite close to what our data actually looks like. So we do a pretty decent job at predicting or capturing what's actually going on in the data. But of course, we can't just go by the kind of eyeball test, so we can do formal model comparison. And indeed, it is the case that the best model has full random effect structure. So these are the BICs, so lower is better. So even though the full random effect structure is, of course, a more complicated model than any of the others, it outperforms it by quite a considerable margin. So what that means psychologically, the lifespan trajectory of vocabulary is nonlinear. It means that people differ in their vocabulary from very early on, at least in this data set. They also differ in where their vocabulary ends up. And by estimating and then extrapolating the shape early on in life, we can better predict the outcomes we care about. So if we essentially know what the shape of development is over time, we can do a better job, say, testing, even if we test people kind of in a high-stakes setting, we can do a better job at estimating their capacity, which might be their job success or educational success, or whatever it is the high stakes is high stakes for. So to summarize, these nonlinear random effects models are flexible and can translate what are often purely verbal theories into tractable models. They're especially useful when you would want to extrapolate beyond what you currently have or your current measurement occasion. You can also apply it to other concepts. So this is very careful analysis done this morning at 9:17 from about 100 kids who were scanned on a remarkable 10 occasions in diffusion weighted imaging. So here we have kind of the reverse. So mean diffusivity in a bunch of kids essentially, of course, goes in the opposite direction, because as white matter matures, MD tends to slow down or tends to decrease. So we can extrapolate these estimates from people's MD, and then essentially you can imagine that the asymptote of white matter development is more maybe in your mid to late 20s, which is kind of what we see. There are many and increasing tools available to estimate these types of models, and there's some really nice hands-on tutorials that I would all recommend you use. And I would also recommend volunteering to give talks about things you want to learn, because Delia and I wanted to learn how to do this, which is why we said we would do it, and we actually taught ourselves to do this pretty much yesterday. Using some of these resources, this wonderful original paper and a follow-on paper that delves a little bit more into the theory and the psychological kind of background, but especially recommended this remarkable resource that has far more than these, but actually hands-on kind of nitty-gritty detailed code and data examples to fit a whole bunch of models, even above and beyond the ones we've talked about today. And on that note, I'd like to end. Thank you very much.